This short video is about the natural logarithm function and eventually about its derivative. So we first have to recap what the natural logarithm function is. And we start out by talking about the number e, which is known as the natural number. And so if we take a logarithm with base e, we can call that the natural logarithm function. So we can see here if we use log base e of x, it's a very commonly used logarithm. So mathematicians have decided that we're going to give it a special name, and we're just going to call it ln. Okay, so instead of saying log base e or log base natural number, we'll just call it ln of x. And we want to notice the relationship between the natural log function and the exponential function. And in fact, anytime we are asking about a logarithm function, what we really want to know is what exponent are we looking for to put on the base that would give us the what we're taking the ln of. Okay, so for example, if I wanted to know what the ln of e squared is, I want to figure out what that is. Well, that would be true. Remember, this is base e, so base raised to what exponent gives me e squared? So in fact, y equals 2. So this has a solution of 2. So anytime we're asking for a logarithm, we really want to know an exponent. What exponent do we want on the base that will give us what we're taking the logarithm of? Okay, so I've given you a couple of examples here. We have the ln of x plus 7, that's a natural log function, the ln of x plus 2 over x plus 1. And we'll take a look at some logarithm properties that will help us when we learn to take derivatives. So that's what we're going to do next. So some properties of logarithms is, there's a couple here that will be useful. The first one is we have the logarithm of a product. So if we take the log of f times g, it turns out it's the log of f plus the log of g, natural log of g. Now remember, it's the relationship between exponents, right? So if we kind of think of if we're multiplying the same base, okay, and we have two different exponents, what do you end up doing? You add the exponents together. So it sort of carries over that property holds for natural logarithms because, like we said, it really is asking for what is the exponent on the base that we would need in order to get f times g. So the way that exponents work corresponds to helping us figure out these properties of logarithms. Similarly, if we have the ln of f divided by g, so the logarithm of a quotient turns into a difference of logarithms. Again, similar to the way exponents work. If you have, x squared over x cubed, you subtract the exponents. So in the same way, log of a quotient, log of a fraction turns into a difference of logarithms. Next one is a sort of an exponent property, that if we have the ln of a function raised to a power, we can bring the power down in front and take the logarithm. It's really just an extension of this here, this very first property, the log of a product, because if we replace g here with f, then we have the ln of f times f, and that would be the ln of f plus the ln of f, which is 2 ln of f. So you can see how powers turn into multiplication. And again, this is algebra, right? This is all algebra. No calculus yet, but we're going to use these algebraic properties when we do our calculus. Okay, and then the last two are the inverse relationships between the natural log function and the natural exponential function. So they are inverses of each other in the same way that the cube root of x cubed is x cube root, and x cubed are inverses. Natural exponential, natural log are inverses of each other. So whatever we're taking the natural log of and then the exponential of, we get out what we started with. Same thing here. If we do exponential function, then we take the log, we get what we started with. Alright, so next thing we want to know is how do we find the derivative of a natural logarithm function? And it's an unusual derivative because a lot of our other derivatives looked similar to what we started with. Like polynomial, you ended up with another polynomial. Exponential function, you ended up with another exponential function. Rational function, you generally ended up with another rational function. So it's interesting that the natural log function, when we take its derivative, so we have the natural log of some function, we call what we're taking the natural log of the argument of the logarithm. And the derivative of the natural log of a function is 1 over the function, or 1 over the argument, times the derivative of that argument. So that's kind of a chain rule, right? We saw when we did the chain rule, general power rule version, you did the power rule, and then you had to multiply by the derivative of the inside. When we did the exponential rule, you rewrote the exponential function times the derivative of the exponent. So it's a similar sort of thing here. And it turns out we can write that as just the derivative of the argument over the argument, or the derivative of the inside function over the inside function. Again, it's a composition of functions. You have a function f of x inside of the logarithm function. So let's try it out. Okay, we have an example here. Y equals the natural log of 2x. So the derivative would be, so remember, it turns up to be a fraction, a rational function here. We just rewrite the argument, so the inside, that 2x, and then we have the derivative of 2x in the numerator. So the derivative of 2x is 2 over 2x. 2 over 2 is 1. So we have 1 over x. We have an equivalent fraction, 1 over x. Okay. All right, let's try the next one here. The ln of x squared minus 2x. So again, the derivative of the logarithm function is always a ratio, a quotient, and in the denominator you always put the argument, the inside function of our composition of functions, and in the numerator goes the derivative of our inside function. So the derivative of x squared minus 2x is 2x minus 2 over x squared minus 2x. And if you'd like, you can factor a 2 out of the numerator, so that would be 2 times x minus 1, and an x out of the denominator, that would be x minus 2. That would pretty much be in the most factored form. It would be most useful for future work. And we've got one more here. The g of x equals the natural log of x plus 1 over x minus 2. Now here's where we're going to take advantage of our algebra. And we're going to use those logarithm properties. So remember, logarithm of a quotient, just like when you have, x cubed over x squared, you subtract the exponents. So natural log of a quotient turns into a difference of natural logs. And then the derivative is just the derivative of each of these terms separately. So the derivative of the natural log of x plus 1, right, is a fraction. X plus 1 goes in the denominator. The derivative of x plus 1 goes in the numerator. And then we've got minus the derivative of the natural log of x plus 2, which is another fraction, with x plus 2 in the denominator this time, right? And the derivative of x plus 2. So let's see. Derivative of x plus 1 is 1 over x plus 1, minus the derivative of x plus 2, which is 1 over x plus 2. And if we wanted, we could get a common denominator and clean that up. But for right now, that's a good enough derivative. So remember, the derivative of the natural log function, notice there is no natural log, right? The derivative of a natural log function, there is no natural log left in the derivative. It is all involving the argument, or the inside function, the function that we are taking the logarithm of, the argument we call it. So derivative of the argument over the argument.